Now, what makes gravity a conservative force is that gravity does not care what path an object takes from its initial vertical position to its final vertical position. The work that gravity does for a given delta y is the same regardless of the path taken. So let's consider an object on a frictionless inclined plane that makes an angle theta with respect to the ground. And let's call the axis of the plane the s-axis. Now, for an object on this frictionless plane, there are two forces acting. We have the force of gravity, which is directed straight towards the ground, and we have a normal force exerted on the object by the surface of the plane that is perpendicular to the surface of the plane. So notice that the only non-zero force is the component of the gravitational force that is parallel to the plane, and this force is equal to negative mg times sine of theta. And so the change in the kinetic energy is equal to the integral from an initial s position to a final s position of negative mg sine theta ds. Now, for a given change in the s coordinate, we have a corresponding change in the y coordinate, which is equal to the change in the s coordinate times the sine of theta. And so the integral from an initial s position to a final s position of negative mg sine theta ds is the integral from an initial y position to a final y position of negative mg dy. Now, the mass and the acceleration due to gravity are constants, so we can bring this out of the integral. So we have negative mg times the integral from an initial y position to a final y position dy. And this is negative mg times the quantity, y final minus y initial, which is negative mg y final plus mg y initial. And this is the same as the initial gravitational potential energy minus the final gravitational potential energy. That is, the final kinetic energy minus the initial kinetic energy is equal to the initial gravitational potential energy minus the final gravitational potential energy. And so the final kinetic energy plus the final gravitational potential energy is equal to the initial kinetic energy plus the initial gravitational potential energy. And this is the same as for an object that falls vertically through the same distance delta y. So notice that if the only force acting is gravity, then the change in the kinetic energy of a system is equal to the negative of the change in the gravitational potential energy of the system. And this is expected since an increase in one comes at the expense of a corresponding decrease in the other. Now, the gravitational potential energy of a system is equal to the negative of the work required to move an object from an initial vertical position to a final vertical position. The negative sign is there since gravity naturally tends to move an object from a higher position to a lower position, and this corresponds to a decrease in the gravitational potential energy of the system. And so this means the work done is positive, and this corresponds to an increase in the kinetic energy of the system. So if the initial height is less than the final height, then the gravitational potential energy of the system increases. And again, this comes at the expense of a decrease in the kinetic energy of the system. And if the initial height is greater than the final height, then the gravitational potential energy of the system decreases, and this results in an increase in the kinetic energy of the system. And of course, if the vertical position does not change, then there is no change in the gravitational potential energy of the system, and so there is also no change in the kinetic energy of the system. So let's look at an example. What minimum speed does a 100-gram puck need to make it to the top of a 3.00 meter long, 20.0 degree frictionless ramp? Okay, so since the ramp is frictionless, we can apply conservation of mechanical energy. So we have 1/2 the mass times the final speed squared plus mg y final is equal to 1/2 m v initial squared plus mg y initial. Now, if the puck just makes it to the top of the ramp, then at the top of the ramp, its final speed is 0. And we can choose our reference frame so that the bottom of the ramp, that is the initial y position, is 0. So we have the simplified equation. The mass times the acceleration due to gravity times the height of the ramp is equal to 1/2 the mass times the initial speed squared. The mass cancels on both sides, solving for the square of the initial speed. We have that the square of the initial speed is 2 times the acceleration due to gravity times the height of the ramp. And so the initial speed is the square root of 2 times the acceleration due to gravity times the height of the ramp. Now this ramp has a length of 3.00 meters, and this ramp is inclined at 20.0 degrees. And so the height of the ramp is 3.00 times the sine of 20 degrees. In units of meters. And so the final speed is the square root of 2 times the acceleration due to gravity, which is 9.80 meters per second squared, times the height of the ramp, which is 3.00 times the sine of 20 degrees in meters. And to 3 significant figures, this is 4.48 meters per second. So as an exercise, a child of mass m starts from rest and slides without friction from a height h along a slide next to a pool. She is launched at an angle theta with respect to the horizontal from a height h divided by 5 over the pool. What is the maximum height she reaches above the water in her projectile motion? Now, a force that restores a system to an equilibrium position is called a restoring force, and systems that exhibit restoring forces are called elastic systems. Common examples include springs and rubber bands. And so a second type of potential energy is elastic potential energy, which is the energy stored in elastic systems such as springs. And according to Hooke's law for springs, the restoring force of a spring is equal to the negative of k times x, where k is the spring constant and x is the position relative to the equilibrium position, which is defined to be 0. Now a spring can be compressed, in which case the position is negative with respect to the equilibrium position, or can be stretched, in which case the position is positive with respect to the equilibrium position. And so the elastic potential energy of the spring is equal to 1/2 kx squared. Notice that the derivative with respect to x of the elastic potential energy for the spring is k times x, which is the negative of the restoring force. Now, because of the x squared term, a spring possesses the same elastic potential energy, whether it is compressed or stretched a given distance from the equilibrium position. And if there is no friction in a spring system and no deformation of the spring, that is, the spring is not stretched or compressed so much that it is no longer a spring, then the mechanical energy of the system is conserved. So let's look at an example. A spring-loaded toy gun launches a 10.0 gram plastic ball. The spring, with spring constant 10.0 newtons per meter, is compressed by 10.0 centimeters as the ball is pushed into the barrel. When the trigger is pulled, the spring is released and shoots the ball back out. What is the ball's speed as it exits the barrel, assuming no friction? Okay, so since there is no friction in the system, and we can assume that the spring is not deformed, we can apply conservation of mechanical energy. And so we have that the final kinetic energy plus the final elastic potential energy of the spring is equal to the initial kinetic energy plus the initial elastic potential energy of the spring. And so we have 1/2 the mass of the ball times the final speed of the ball plus 1/2 the spring constant times the final position relative to equilibrium squared is equal to 1/2 the mass times the initial speed squared plus 1/2 the spring constant k times the initial position squared. Now, when the spring is released, it returns to its equilibrium position. And when the ball is loaded, it is initially at rest. And so we have a simplified equation. 1/2 the mass of the ball times its speed squared is equal to 1/2 the spring constant times the initial compression squared. We can eliminate 1/2 from both sides of the equation. Solving for the square of the speed, we have the speed squared is equal to the spring constant k times the compression squared divided by the mass. And so the speed is equal to the square root of the spring constant times the amount of compression squared over the mass. And so the speed of the ball as it exits the barrel is the square root of the spring constant, which is 10.0 newtons per meter, times the square of the compression, which is 10.0 centimeters, or 1.00 times 10 to the negative first meters squared, divided by the mass of the ball, which is 10.0 grams, or 1.00 times 10 to the negative second kilograms. And to three significant figures, this is 3.16 meters per second. Now, if both gravity and a restoring force act in a system, then the total potential energy is the sum of the gravitational potential energy and the elastic potential energy. And if the mechanical energy of such a system is conserved, then the change in the kinetic energy is equal to the negative of the change in the total potential energy. We can rewrite this equation in the form: the sum of the change in the kinetic energy plus the change in the gravitational potential energy plus the change in the elastic potential energy is 0. So let's look at another example. An inclined plane of angle theta equal to 20.0 degrees has a spring of force constant K equal to 500 newtons per meter fastened securely at the bottom so that the spring is parallel to the surface. A block of mass m equal to 2.50 kilograms is placed on the plane at a distance d equal to 0.300 meters from the spring. From this position, the block is projected downwards toward the spring with speed equal to 0.750 meters per second. By what distance is the spring compressed when the block momentarily comes to rest? We will assume that there is no friction on the plane and that the spring is not deformed. So we can apply conservation of mechanical energy. And so we have 1/2 the mass times the quantity, the final speed squared minus the initial speed squared, plus the mass times the acceleration due to gravity times the quantity, the final height minus the initial height, plus 1/2 the spring constant K times the quantity, the final position squared minus the initial position squared, is equal to 0. Now in the final state, the block is at rest. We can choose our reference frame so that the final height is 0. And in the initial state, the spring is in its equilibrium position. And so we have the simplified equation, negative 1/2 the mass times the initial speed squared, minus the mass times the acceleration due to gravity times the initial height, plus 1/2 the spring constant times the final position squared is equal to 0. Now we need to determine the initial height in our reference frame. Now the block moves through a distance d plus a distance that is equal to the magnitude of the compression, which is the negative of the final position, since it is a compression. And so our initial height is the vertical distance between its initial position and the position of the compressed spring. And so the initial height is the quantity, d minus the initial position times the the final position times the sine of 20 degrees. And so our equation is 1/2 kx sub f squared minus mg times the quantity, d minus x sub f times the sine of 20 degrees, minus 1/2 mv initial squared is equal to 0. So we have 1/2 kx sub f squared plus mg times the sine of 20 degrees times x sub f minus m times g times d times the sine of 20 degrees minus 1/2 mv initial squared is equal to 0. And we can rewrite this equation as 1/2 kx sub f squared plus mg sine of 20 degrees times x sub f minus the quantity 2 times mgd times the sine of 20 plus the mass times the initial speed squared, all of which is divided by 2, and this entire expression is equal to 0. Now this is a quadratic equation, and so we can solve it using the quadratic formula. Now this is a very bulky equation, so I'm going to break it into parts. So first we'll find the determinant, which is the b squared minus 4ac term. So we have m squared g squared times the square of the sine of 20. Now 4 times the coefficient of the square term is 2 times k. 2 times k divided by 2 is k. A negative and a negative makes a positive, and so this is plus k times the quantity 2mgd sine of 20 plus mv initial squared. And so the final position is the negative of mg sine of 20 plus or minus the square root of the determinant, all of which is divided by 2 times the coefficient of the square, which is k. Now we want the negative value, and so we choose the negative or minus the square root of the determinant. And if we plug all these values into the calculator correctly, we have negative 1.31 times 10 to the negative first meters, or negative 13.1 centimeters. That is, the spring is compressed by 13.1 centimeters. And you can also use a computer algebra system such as the free GeoGebra. Simply enter the equation. And remember that you want the negative value, so we can zoom in. Until we get the desired accuracy. And so to three significant figures, we have negative 0.131.